In this tutorial, we'll explore dependency measures and some of their advantages and disadvantages. Dependency between financial securities refers to their relationship to one another and if they move up and down together. Uses of dependence measures often occur in portfolio construction, asset allocation, risk management, and hedging. One of the most common measurements used in practice is correlation. Correlation is an effective tool for measuring linear relationships and uses the following formula. Correlation values range from -1 to +1. A +1 would indicate a perfectly positive linear relationship. When security A has positive returns, so does security B, and vice versa for negative returns. A value of -1 would be a perfectly negative linear relationship. A value of positive 0.6 would still indicate a relatively strong positive relationship, while a value of 0 indicates no relationship, either positive or negative. Correlation is a necessary input for one of the most traditional allocation models, known as modern portfolio theory. In this model, risk is measured by covariance, which describes risk well provided returns are normally distributed. While this is one limitation for MPT, another limitation of correlation is that while it works well for linear relationships, it does not describe nonlinear relationships well. The next dependence measure we'll discuss is known as a copula. A copula is a mathematical function that relates percentiles, or ranks, of one variable to the percentiles of another. There are many different types of copulas, but for the scope of this tutorial, we'll focus on two: the Gaussian copula and the student T copula. For example, a Gaussian copula may take the following visual relationship. Notice in this example, there's a positive relationship, similar to a positive correlation. In reality, they are not very dissimilar. However, notice the axes. They both range from 0 to 1. We are now relating the percentiles, or relative ranks, of two financial securities. In words, this means the highest returns correspond with the highest returns of the second security. This sounds similar to correlation, but specifically it is now measured by rank correlation. Two measurements of rank correlation are common: Spearman's rho and Kendall's tau. One of the advantages of using a copula is that the dependence relationship now will not be affected by any assumptions in the return distributions. Recall, using correlation in MPT is well suited for normal distributions. However, many financial distributions are non-normal. Therefore, correlation and its MPT risk measurement, covariance, may not adequately model the underlying risk of financial returns. One method around this is to model a Gaussian copula, which can simulate related rankings. The relationship between rankings is always the same, regardless of what distribution the financial returns take. Therefore, any distribution model can be applied to the financial returns. Combined with our simulated rankings from the Gaussian copula, we can simulate security returns that are related and still account for fat-tail distributions and skewness. Gaussian copulas were popular prior to the 2008 financial crisis and received poor publicity afterward. While Gaussian copulas provide more flexibility than linear correlation, it still suffers one of the same limitations. The Gaussian copula still models, generally, a linear relationship. In the 2008 financial crisis, however, when one asset class begins to have extreme negative returns, other asset classes experience the same. In down markets, correlation increases. Neither linear correlation nor Gaussian copulas account for this phenomenon. The next copula we'll discuss, the student T copula, can model this effect. The student T copula has a second parameter, in addition to rank correlation, called degrees of freedom. The lower this parameter value, the stronger the dependence of tail or extreme observations. For example, with the degrees of freedom of 6, the student T copula will model an increasing correlation of results at both the extreme lows and highs. To illustrate this effect, we need to first introduce a measurement known as tail index. Tail index is a statistical formula to measure the dependence of extreme events. This measurement ranges from 0 to 1. 0 indicates no change in relationship when extreme events occur. Higher values indicate stronger relationships during extreme events. Using our example, the Gaussian copula has a tail index of 0, while the student T copula models an increase in tail dependency with values closer to 1 for this pair of securities. In the fitting distributions tutorial, we discussed evaluating the quality of fit using likelihood measurements and AIC. These same tools can be applied to validate that the student T copula models the dependency better than the Gaussian copula in this case. Finally, we cover the concept of dynamic measures of dependency. Initial approaches to this idea involve using rolling linear correlations. However, new mathematical tools are available that compute conditional correlation, similar to the method used to compute conditional volatility in Garch modeling. This approach involves more sophisticated mathematics and computing power. The result, however, can provide a quick view as to how correlation changes through time. This completes the dependence measures tutorial.